Hello, hi everyone. So this is Ken 422, Chemical Reaction Engineering, week number 8, October 13th. Today we'll be talking about series reactions, or it's also the chapter in Levenspiel, chapter 8. Just talking about series reactions and, having series and parallel reactions at the same time and other types of situations. Homework 6 will be assigned today. Take your time and do it. It covers both chapter 7 and chapter 8. A lot of it is sort of qualitative and trying to understand, trying to gauge or give you some practice to think about how the mixing patterns affect the reaction performance and the reaction extent. So, try to do it. And I'm going to post the solutions video later today as well. And again, if you have any questions, please come to office hours. Okay, so just to update you on the schedule. So last week we talked about parallel reactions. This week we'll talk about series reactions. Next week, hopefully we'll talk about temperature and pressure effects. And then we're gonna have a review week. And then finally, we're gonna have exam 2. And again, exam 2, we'll talk about it as we get closer, but it will cover basically these 3 topics. All right. So let's start off talking about the different classes of multiple reactions. So you have parallel reactions, where basically A goes to R and A goes to S. The 2 reactions happen in parallel to each other, right? And then we also have a series reaction right here where A goes to R and intermediate, and then goes to S as a second step, or reacts further to go to S. And this type of reaction is of interest, especially if I want to control the production of R, if I want to maximize the production of R, or if R is the product of choice, right? The third type of multiple reactions you see here, where I have A plus B goes to R, and then R plus B goes to S. So you can see this system of reactions is series with respect to A. So A plus B goes to R, and then R goes to S, and it's parallel with respect to B. So B reacts with both A and R, giving me 2 different products. And this type of system is highly dependent on the mixing pattern and how you really control the way you introduce the different species into your reactor. And we're going to talk about it today. Okay. So let's take some examples just to give you some realistic or, some common type of reactions. So here I have nitration of benzene. I have benzene reacting with nitric acid in the presence of H2SO4. This reaction usually occurs at 50 Celsius, something like that, not too high of a temperature. I get nitrobenzene, which is a common solvent, plus water as a byproduct. However, nitrobenzene will still want to react with more of the nitric acid to give me dinitrobenzene, right? I get NO2 at both 2 sort of edges of the benzene ring. And again, this will still want to eat up some more of the nitric acid to give me 3 or trinitrobenzene, right? And if we look at this reaction, it's a series with respect to A, because A goes to R, goes to S, goes to T. And it's parallel with respect to B, because, this nitric acid wants to react with any of the benzenes, whether it's, benzene, nitrobenzene, dinitrobenzene. And if nitrobenzene is my desired product, so if you're in a plant and you want to maximize the production of this guy, how can you avoid getting these 2 in large quantities in your product streams? And of course, it depends on your reaction rates, obviously. So, it depends on the ratio of K1 to K2 to K3. And it also depends on the amount of concentration available of nitric acid, of this species, of that species, whatever. So if I can control these concentrations using some sort of mixing strategy or mixing pattern, I can achieve my objective. Again, similarly, a second type of very common reaction you see here, hydrolysis of ethylene oxide from glycols. So I have ethylene oxide, I add water to get, ethylene glycol, or, monoethylene glycol. Monoethylene glycol reacts with ethylene oxide to give me diethylene glycol. However, and then diethylene glycol reacts again with ethylene oxide to give me triethylene glycol, okay? And these glycols are very common industrial solvents, coolants, used in many applications. And again, this type of reaction is series with respect to A, parallel with series for A, and it's also parallel for A. And it's a unique system. So if I want to maximize, let's say, the production of S, how can you do it, or what strategies can you do it, etc. And of course, if you think about it, take your time. I'm sure you can come up with a bunch of strategies. A lot of these strategies are sort of logical, but once you get into the thinking pattern of achieving it, it becomes more obvious. Okay, so in order to introduce this type of thought, let's take a motivating example. So let's consider this type of reaction where I have A goes to R and R goes to S. The reaction A to R has a reaction rate of K1. The reaction R to S has a reaction rate of K2. And R is the desired product. So I want to maximize the production of R in this case. A couple of things to note: the reaction proceeds only in the presence of light. So this is a photoreaction or photocatalytic reaction if you want. And reaction stops the instant the light is turned off. Okay, so I have this reaction. It only proceeds when light is turned on. Once I switch off the light, reaction stops. What approaches can you take to control the product distribution? So how can I control the system so that I maximize the production of R? So let's take a look at two approaches. First approach right here, I have my, my A, right? It only starts with A. It's very well mixed, and I have light turned on. And in this approach, the concentration of the beaker are irradiated uniformly. So I always have the light on. I always have a very good mixing strategy. So all the components of the reactor are all receiving the same amount of light. And the reaction rate depends on the concentration and irradiation. So if I take a look at concentration in beaker versus the time since light was turned on. So initially here, time equals 0. I only have A and the light is turned on. Because it's a photocatalytic reaction, or a photoreaction, A starts decreasing and R starts increasing. So I'm saying this part, A is being converted to R, and eventually, and I have some S as well, but it's not as much because the amount of R available is still not very high. Eventually, the amount of R reaches a maximum, and at this point, I have enough R to compete with A for the light. So R will there's a lot of R in the beaker compared to A. So R will start taking the lead in this reaction. So this second part will start taking over, and then the R will start reacting more, and we'll start seeing more S, right? And this is really the extreme to achieve the maximum amount of R. So in order to achieve the maximum amount of R, this is really the best strategy to use. And ideally, I would try to stop the light or stop the reaction once I get to this point. Maybe once I get to this point, depending on how easy it is to separate these products, right? Let's have a look at the other extreme, second end of this reaction. So the second approach, I'm taking a small stream from my batch reactor, I'm pumping it, and I'm introducing it to a glass tube, which is irradiated. And then I'm returning the converted products back into my beaker, right? So a small stream is continuously withdrawn, irradiated, and returned to beaker. So there is no light or no irradiation directly at the beaker. I'm only reacting a small slipstream from the beaker. And if I take a look at the products, and in this case, so I have A. This is the concentration in the beaker. Initially, it's only A, and then A will drop and S will increase. As you notice, there is no R because I take a small amount of A here. I reacted completely to S, and I'm only returning S back to the beaker, right? So the amount of R available in the beaker is very low, almost 0. And this is the other extreme where I have 0 R, right? Compared to approach 1, where I had a maximum amount of R. And these two scenarios give you an idea about the approaches you could use to try to maximize the conversion of this intermediate species. So when we think about it, which approach is better? These two approaches represent the two extremes in the possible operation. Approach number 1, where I'm mixing very well and I'm irradiating the entire beaker. I get the maximum possible formation of the R. The contents remain homogeneous and slowly change with time, right? And then approach number 1, you can see that A decreases, R reaches a maximum, and then after R reaches a maximum, S starts picking up and R decreases. Approach number 2, there is minimum or no formation of R. I don't get any R because I'm taking a small stream, reacting it completely to S, just returning S back into my beaker. This is highly reactive fluid, is continuously mixed with fresh fluid, i.e. I'm mixing two streams of different compositions. So using this thought experiment and using these two extremes, we can see, or we can make a preliminary conclusion saying that if I mix two streams of different compositions, or the more mixing I have of streams of different compositions, the less formation of intermediate I'm gonna get, right? And this is really the governing principle behind a lot of these strategies. So for irreversible reactions, avoiding mixing, for reversible reactions, maybe a comma here, avoiding mixing of fluids of different compositions is the key to forming the maximum of the intermediate. Okay, so if I want to maximize my intermediate, I want to avoid mixing fluids of different compositions. Okay, and approach number 1 achieves this because I only have one fluid in my beaker, it's homogeneous, and I'm just constantly mixing it. Whereas in approach number 2, I have constant mixing of fluids of different compositions. And the maximum amount of any intermediate is obtained when fluids of different compositions and at different stages of convergence are not allowed to mix. Okay, so again, if I want to maximize my intermediate, I want to minimize mixing of fluids of different compositions and different conversions, right? And just note the difference here. I'm talking about mixing of two different streams. I'm not talking about maintaining homogeneity inside your reactor. Two different ideas. However, if I want to maximize the presence of an intermediate, I want to minimize or present mixing of two different streams or two different fluids, different compositions, different conversions. Okay. So let's have a look at some examples here. I have a reaction, A going to R going to S, and I have 4 problems, right? Where I want to compare which one of these, you know, which reactor, the right on the left or the left, was better for making lots of R or maximizing the production of R. And I have 4 problems or 4 scenarios here for comparisons to make, and we're gonna take a look at them one by one. And again, the governing principle is I want to minimize mixing of fluids of different compositions or different conversions. So let's have a look at part A, where I'm looking between a plug flow reactor and a CSTR. And the plug flow reactor is always the better option to maximize the production of your intermediate, because in a plug flow, fluids of different compositions and at different stages of convergence are not allowed to mix. Because if you recall, we said in a plug flow, the easiest way or the way to think about it is like different or separate plugs or separate maybe small cylinders of fluid are just pushing each other. There is no mixing along the direction of flow. So the fluid at this stage, or even though it will have a different conversion, it's not back mixing with the fluid at this point. Basically a plug flow reactor will always give you a higher concentration of intermediate compared to a CSTR, or even though in a CSTR it's a homogeneous system, I have a lot of mixing. However, I have more mixing of fluids of different concentrations, different conversions compared to a PFR. And this is really the most ideal option, or the best option, best flow scheme to maximize the intermediate performance. So therefore, to maximize intermediate concentration, system performance should approach ideal PFR performance. And always remember this when maybe in a multiple choice question or when you're generally thinking about these systems. In order to maximize your concentration of intermediate, your system should always approach PFR performance or ideal plug flow reactor performance, i.e. I have very little mixing in the direction of flow. I have very little mixing between elements having different concentrations, and I have very little or no mixing between elements having different conversions, right? So a small cylinder right here will travel all the way and never interact with any of the previous cylinders. There is no mixing in the direction of flow. A CSTR will be better than a batch flow reactor in performance, of course. However, compared to a PFR, it performs, it's not as good. compared to a PFR. Okay. Let's have a look at the second scenario. So in the second scenario, I'm comparing a plug flow reactor with a recycle compared to CSTRs in series. And okay, here we're thinking, if you think back about your previous lectures, you know, a PFR with a recycle, as the recycle approaches zero, PFR, or you know, the system behaves as an ideal PFR, and as the recycle approaches infinity, the system behaves as a CSTR, right? If you recall, in one of the previous lectures, said, you know, as R approaches maybe very high number, this plug flow reactor performance approaches a CSTR compared to having CSTRs in series. And we also said previously that having CSTRs in series, their performance approaches that of a PFR. So here we'll also have some comparisons, and in this type of comparison where, you know, this performance of the system approaches that of a PFR, and here the recycle ratio really governs the performance of the plug flow reactor. We have to look at the reaction kinetics, right? And we have to look at the order of the reaction. But always remember that having a recycle is a better option to maximize the intermediate for positive order reactions. So if you have a positive order reaction, a PFR with a recycle will give you more intermediate compared to CSTRs in series. Okay, third case, I'm comparing CSTRs. They're both in series. However, here I have sort of a my feed is being distributed equally among these CSTRs. So they are in series. However, there's also a parallel element to it. Whereas here they are purely in series. Just the feed enters, reacts, gets pushed to a second CSTR, moves on. And this system on the right-hand side is the better performance because this behaves closer to a PFR compared to the system on the left-hand side, right? So the system on the left-hand side actually performs closer to a larger CSTR with an equivalent volume, right? Because I'm just equally distributing the feed among these two guys, and I'm minimizing the PFR. I'm minimizing the effect of having them in series to approach a PFR performance, right? So this system is actually closer to a large CSTR compared to this system, which is actually closer to a PFR. And again, want to maximize intermediate, you want your performance to approach that of a PFR always. And then finally, and again, this is a bit tricky, but just know it, that if I have a PFR operating in laminar flow versus turbulent flow will always give you a higher intermediate. And the logic here is that turbulent flow, you'll have less mixing along the flow direction and more mixing along the axial direction, okay? Because therefore you have less bypassing of fluids and you have less overall mixing of fluids of different concentrations and different conversions. And just remember that when you have a turbulent flow, even though logically you might think, oh, it's turbulent, I have mixing everywhere, all the elements are mixed together. This is not the real behavior in these types of reactor. You need to think about the length of the eddies. For example, you know, in a laminar flow reactor, you have larger eddies which are slower. So these larger eddies tend to span the length of the reactor compared to a turbulent flow reactor or turbulent flow regime, where I have a lot of small eddies. A lot of them create a lot of local mixing. You don't see a lot of wide, large eddies which span the entire length of the reactor, right? So here I have a lot of small eddies, small local mixing occurring in all the elements. So the reactor is well mixed in every plug, but there's minimal mixing really between the front and the back of the reactor, or the start and the end of the reactor, compared to laminar flow, where I tend to have large eddies, right? And these large eddies create sort of a convective flow effect, and you tend to have more mixing between the different elements or along the flow direction. So again, in a PFR, you want operating in a turbulent flow regime will always give you more intermediate compared to operating in a laminar flow regime. So just know this, understand the reasoning, and try not to forget. Okay. So let's have a look at some quantitative analysis. So let's try to quantify it. So, and here what you really need to remember are these two equations, but let's go through this. So if you have a reaction or a series reaction A going to R going to S in a plug flow or batch reactor, and assuming no reaction products in the feed. So initially I only have A in a batch reactor and a plug flow reactor, only A, and it's reacting. There is no R, there is no S. If you do the derivations, you can do these derivations again. We've seen this equation before. You can do these derivations. However, what I'm really interested in, and you can read them in your book, are these two like performance equations here, or these two governing equations. And please take note of them. You might have to use them at some point, but it's important to know them. And just before we move on, T in an IBR is equivalent to tau in a PFR. Okay, just remember this, we've talked about this before. So in a PFR, A going to R going to S, I have two equations which you need to know. First equation here, as you can see, is the concentration, maximum concentration of R, CR max over CA naught, which is the initial concentration of A, is equal to K1 over K2. K1 is the reaction rate for this equation. K2 is the reaction rate for this reaction, sorry. K1 over K2 to the power of K2 over K2 minus K1. And this is the equation which will determine the maximum concentration of intermediate in a PFR, right? So if I want to determine the maximum concentration of R, I have my reaction rates, I plug in my numbers, I get my CR max. Okay, similarly, this is on the right-hand side here, this is the equation to determine the time at which the maximum intermediate occurs, okay? And second, yeah, so tau, and this is tau optimum, OPT stands for optimum, and this equation here will determine the time at which the maximum intermediate concentration occurs, or the time at which you see CR max. If you recall, previously we showed these charts talking about approach number 1 here. So these two equations will give you your CR max, or the concentration at the maximum point, and the time at which this occurs. And this will help you, or you can use this to determine how you want to operate the system. Let's go back here a bit. So please know these two equations. And again, the tau, optimum tau, again, is a function of my reaction rate constants. Ln K2 over K1 over K2 minus K1, K2, K1, K2 minus. And again, this is for an ideal system. If you go to grad school, or if you, become a technologist for a reactor, whatever it is, there are a lot of different correction factors, a lot of different supplementary equations, whatever, which account for the nature of the fluid, viscosity, density, all this stuff, thermodynamics, which can also come into play here. But generally, for our ideal case, these two reactions, take note of them, and just remember them for a PFR or a batch reactor. Okay, and these equations basically plot your the concentration as a function of K1 tau and as a function of X1. You can always, if you want, you can read off these charts. It's up to you. 2 lines to note is this dashed line here. It's the locus for CR max, and again this dashed line also here, the locus for CR max. And as you can see, as the ratio of K2 over K1 changes, this behavior of C over CA naught varies significantly. Okay, take a look at these charts, maybe try to look at some patterns, etc. You can read off them in the test, but they are basically a depiction of the equations shown previously. Okay, second thing we're looking at is for a CSTR. So let's do a quantitative analysis for a CSTR. Again, A goes to R goes to S. I'm assuming no reaction products of R or S in the feed. So I have 2 governing equations similarly. First one is for time, so tau for a mixed reactor, the optimum time, and this is the equation to determine the time at which the maximum intermediate concentration is present in a CSTR. So this is the time at which I have R max in a CSTR, or CR max in a CSTR, and this is basically 1 over radical or square root of K1, K2. K1 is the reaction rate constant for this first reaction, K2 is the reaction rate constant for this second reaction. Similarly, I have an equation to determine the maximum concentration of intermediate, CR max over CA naught. This is equal to 1 over K2 over K1 to the half plus 1 squared, and this equation will give me the maximum concentration of my intermediate R in a CSTR, okay? So take note of these two equations as well to determine the maximum concentration and the time at which this occurs in a CSTR. And similarly, these plots show the above equations graphically. And again, just take a look at the different trends, try to, maybe think about it and how the ratio of K2 over K1 affects this C over CA naught. And you can read off it directly if you want as well. It's just plotting the same equation. Okay. So we compare the fractional yields in a CSTR and a PFR for various ratios of K2 over K1. So as you can see here on the left-hand side, or on the y-axis, sorry, I'm plotting the fractional yield of R, so R over R plus S, or R over A. It's basically the concentration of R over the initial concentration of A minus the concentration of A at any time t, versus the conversion of A. So I'm looking at the fractional yield versus the conversion. I have two sets of lines. The pink lines or the dashed lines are for the mixed flow reactors or for your CSTR, and the black lines are for the PFR. And as you can see here, for a specific XA and K2 over K1, the PFR will always give you a higher yield of the desired intermediate R. So if I look at these lines, let's look at this pair right here. K2 over K1 is 0.1, and the black line will always give me a higher fractional yield compared to the dashed line, which means that the PFR will always give me a higher concentration of intermediate compared to the CSTR. Similarly, for K2 over K1 is 1, the solid black line is higher than the dashed pink line, and similarly for K2 over K1 equals 10, the solid black line is always higher than the dashed pink line. And this reiterates what we said previously, that if you want to maximize the concentration of your intermediate, you always want your performance to approach that of a PFR as much as possible. Okay. And then there are some specific cases. I highly recommend you read them in Levenspiel section 8.2 for when you have a first order followed by a zero order reaction. Basically K1, A goes to R. It's a first order reaction, then R goes to S. This is a zero order reaction. Read them in Levenspiel. What happens is basically we take the equations we previously showed and they just rederive them, or they just simplify them for having one of the reaction being a zero order reaction. Similarly, having a zero order followed by a first order reaction, again, there's also a special case. Please read it in Levenspiel sections 8.2 and 8.3. They're only a couple of pages, but yeah, just go over them to get a better understanding of them. And it's just, I'm trying to go over the math and see how having a zero order reaction affects these equations, which we showed above. Okay. So now let's talk about some qualitative ideas when we're comparing the mixing patterns versus the product distribution. The first thing, so in this case, let's say I have a two-step irreversible series parallel reaction. So we've talked about series reactions, we've talked about parallel reactions. Let's talk about a system where I have both series and parallel reactions at the same time. And so in this case, I have A plus B going to R with a reaction rate constant of K1, and R plus B going to S with a reaction rate constant of K2. This system is series with respect to A, so A goes to R, R goes to S, and it's parallel with respect to B, because B reacts with both A and R to give me two products, R and S. And I'm gonna qualitatively discuss the product distribution and the effect of the mixing pattern on the product distribution. So the first strategy we're looking at, I have a beaker full of pure B, and it's very well mixed, and I'm slowly adding A to this beaker, right? I have this beaker, only B initially, there is no A, nothing in it, only pure B, mixing very well, and I'm slowly introducing A dropwise. And let's look here, and this graph here shows you the amount of B in the beaker versus the moles of A added. Basically, you can think of it as concentration versus time if you want, but this is how it is. So what happens initially? So initially I have just pure B. I'm adding A slowly dropwise, and when I add A slowly dropwise, all the A gets used up, right? And all the A gets used up to make R. So I'm at this point, I add, let's say, 1 drop of A. A is just 1 drop in a sea of B, right? It gets completely reacted to R. However, R finds itself in the same situation. It's completely surrounded by B, so it completely moves to S. So I slowly keep on adding B. Sorry, I slowly keep on adding A goes to R, and then R completely reacts to S. And as you can see here, the concentration of B will slowly drop and the concentration of S will slowly increase. I'm not getting any R in this situation. And then eventually, after some time, when I have a lot of S or when the concentration of B drops significantly, I start getting more A building up in the system, right? Because now, B reacts completely, and then just I'm just pouring A into the system, and A is not reacting with S, really. There is no A plus S in the system. And this mixing pattern will give you no intermediate, right? Because I'm slowly adding A into the B, the reaction is in series with respect to A and parallel with respect to B. Always remember this. So if I'm adding the component to which the reaction is in series with, and basically A finds itself surrounded by B. B is in complete excess, so A goes to R. However, R finds itself also in complete excess of B, so it completely moves to S, right? There is no competition between A and R at any point in the system for this reaction to for R to build up. And in this way, I'm getting no intermediate. So this is one way to mix these types of systems. And if you mix it this way, I'm getting no intermediate. So if you're targeting S and you want pure S, you don't want to get any intermediate or any byproducts, you use the strategy. You have a beaker full of the species which the system is parallel to, and then you slowly introduce the species which the system is in series to. This way you get no intermediate and you only get pure product of S. Okay, let's have a look at the second situation. Again, same system, A plus B going to R, and R plus B going to S. In this case, I'm doing the opposite actually. I have a beaker full of A, well mixed, and I'm adding B droplet-wise into the system. Okay, so in this case, let's have a look at the concentration of materials versus conversion, or this also, delta B, or amount to be consumed versus time. And in this case, you can see that A initially it's only A, and there's 0 B. I add a drop of B, it gets completely converted to R, right? So I add a drop of B, it gets completely converted to R. There isn't enough B for S to form, or there is a very small amount of B. So R starts building up, right? Eventually, until R reaches a critical concentration or a maximum concentration, where every time I add a drop of B, now A and R are both competing for B, right? So now S starts to form, and the amount of S increases, the amount of R decreases. And this type of system or this type of strategy you can use to maximize the production of your intermediate. So if I use the strategy where I have initially the beaker or my batch reactor or my CSTR, whatever it is full of the species to which this reaction is in series to, and I'm adding the species which the reaction is in parallel to in droplet form, or in a very small quantity or in a limiting quantity, etc., I can get a maximum concentration of the intermediate. And if I know when to stop the reaction, or if I do my calculations properly, I know my reaction kinetics properly, I would be able to identify the point, whether it's delta P, whether it's time, whether it's conversion, whatever, to stop this reaction at the stage where I maximize the concentration of R. And of course, you're going to have a separation step here. Unless you're comfortable, you can maybe stop it here, and you're comfortable with this amount of impurity, and then you only have one separation versus two separations. But these are all considerations for other types of courses. But basically, this type of strategy will maximize the production of your intermediate as long as you stop it at the right time. So think about these two strategies, and these two strategies are, think about it, they're very similar to what we talked at the beginning of the lecture, but think about it, and if you have any questions, come to office hours. Again, the third strategy is I have a container and I just dump A and B in them, very well mixed, and just let it happen, let the reaction happen. And this type of approach will give me the same behavior as, will give me the same basically profile shown on this chart, because I dump all of A and B, A and B start react, so A and B will start reacting to make R, and then eventually once I have a high enough concentration of R to compete with A, R and B will react to give me S, etc. However, the problem with this type of system is you have zero control on when to stop the reaction, right? You just dump everything here. You have to wait until the reaction reaches the end point. Whereas here, it gives you more control. So if you're monitoring the concentrations, you can stop here and say, okay, this is good enough. Let's stop here and let's take this product, or maybe want to stop here, etc. But these two strategies will give you the same type of performance. Okay, so let's take a look at some conclusions for this chapter. So if I have a reaction which is in series with respect to A and parallel with respect to B, A plus B going to R plus B going to S. For maximum CR, keep all A at a uniform composition at all times. So if I want to maximize concentration of R, I want to keep A at a uniform composition, and it's the same as making it as a simple reaction in series. So I'm trying to introduce B slowly or to maximize CR, which is what we talked about in the previous slide. I'm introducing B slowly to keep A at a very high concentration at all times. Second conclusion, the concentration level of CB has no effect on the product distribution. And again, look at the previous slides and convince yourself of this conclusion. So basically, concentration of CB won't have a big effect on the product distribution. What really has a big effect is the concentration of CA, right? And then we're going to propose a final rule. Reversible series parallel reactions can be analyzed in terms of their constituent series reaction, constituent parallel reactions, and that the optimum contacting for favorable product distribution is the same as for the constituent reactions. So basically, when you think about it, we talked about the two mixing patterns. The first one here, I have a beaker full of the species, which is in parallel, and I'm introducing the species, which is in series. And this mixing pattern will basically maximize the production of the final product and give me zero intermediate, versus I have a beaker full of the species, which is in series, and I'm introducing the species, which is in parallel in a very slow manner. And this type of strategy will give me the maximum possible concentration of R. However, I have to be able to control it to stop it at the point which helps your process. Okay, so this is the end of this week's lectures. Again, it's a bit of a short lecture. Try to understand these scenarios, try to understand the effect of the mixing pattern, take time and try to think about this stuff and try to visualize it, etc. Homework number 6 will be posted today. It's a long homework. You have 10 days to do it. I'm going to post the solutions later today as well. And please come to office hours if you have any questions. This will feature heavily on your second exam. And yeah, don't hesitate to reach out if you have any questions, you want any clarifications, you want to set a meeting to talk about this further, etc. Thank you very much.